Hi, welcome to Algebra 2 Common Core. Now that we've covered all the formulas for sequences and series in Unit 5, let's take a look at a few application problems having to do with all of those formulas. So let's start with exercise number 1. It specifies that in 2010 the population of New York State was approximately 19,378,000, and we are given that the growth rate is 1.5%. So with that growth rate, we know that we are talking about a R value of 0.015. So that tells me that in my geometric sequence, that's going to be 1.015 multiplied by each previous term. Again, notice that we're using a different definition of R. When we're talking exponential, the R gets added to 1 when I've got growth rate to give me that 1.015. When I'm talking about a geometric series, then it means what do I have to multiply each term by to get the next term. So in that case, 1.015 stands for the R in the geometric series. Assuming that this growth rate is maintained for a large number of years, which equation can be used to predict the population of New York T years after 2010? Now, the key to this problem is how the time is specified. So T stands for the number of years since 2010. What that tells me, if I come off to the side here, I know that when T is equal to 0, that stands for the year 2010, and I know that the population right then is going to be my original number, 19,378,000. So if I go 1 year later, T equals 1, would then specify 2011, and then my population is going to be what I had before, 19,378,000, multiplied by one factor of 1.015. Let's go one more. If T is equal to 2, that tells me that I'm talking about the year 2012. So in that case, P is going to be equal to that 19,378,000 multiplied by 1.015, this time to the second power. So you can see the pattern that's going to tell us how we get the population for any value of T. So let's look at these multiple choice answers and see which one makes sense according to the time and population that we know has to happen. In choice number 1, we see that we're starting with the population, 19,378,000. But if we look carefully, I don't think we want to multiply the number of years times 1.015. So that tells me that this one doesn't make sense at all. I'm going to cross that one off. If I look at choice number 2, this one looks really promising because I see that my population is being multiplied by some number of factors 1.015. But let's really take a careful look at this one. So for example, if I've got that T is equal to 0, that would mean P of 0 would be equal to 19,378,000 multiplied by 1.015 to the 0 minus 1, which is negative 1. That makes my 1.015 being raised to the negative 1 turn out to be a fraction, and that's not what I want. Let's go further and see what happens at time 1. When T is 1, I'm seeing that I'm getting my 19,378,000, but this time I'm multiplying by 1.015 to the 1 minus 1, which is 0. Well, anything to the 0 power gives me 1, so that brings me back to my original population. And I know, according to what I just figured out, that when T is 1, my population already has to be multiplied by 1.015. So this one, because of the subscripts, seems to be wrong. For choice 3, notice that I'm Starting with my original population, so this is a recursive definition, but to figure out my answer, am I taking my population and multiplying by 1.015 and then also adding it on to the original? No, that means I'm counting my original population twice. Once here, and once when I multiply by the 1.015. So this can't possibly work either. Let's see why choice number 4 does work. If I've got my original population as my 19 million, and then any subsequent population, so for example, let's try the next one. P1 would be multiplied by 1.015 times the original population. So that seems to make sense. P1 should be the original population multiplied by 1.015. If I want P2, that should be 1.015 multiplied by the population in year number 1. So yes, each time I'm going to the next year, I'm multiplying the previous year by 1.015. So here is the correct answer for that question. In exercise number 2, we encounter a pretty common type of sequence and series type problem. Kristen wants to increase her running endurance. According to experts, a gradual mileage increase of 10% per year can reduce the risk of injury. So we see that our increase is 10%. Of course, what that's going to mean is that my R value is going to be 1.10. And again, I'm talking a different R than I was talking back in my exponential growth problems. This R stands for what I'm going to multiply the current week by to get the next week's amount of miles that she runs. So R is equal to 1.10 because she's increasing by 10%. Now, we know that she's starting with 8 miles in week number 1, so that means that A1 must be equal to 8. And we want to figure out what's a formula that we can use, a geometric series formula, in order to come up with her total mileage over n weeks. So let's start with those geometric series formulas. So we know that S, notice that we're doing it in the general state right now. So S means the total amount over n weeks is going to be equal to, let's go back to that geometric series formula. So we have to have our A1, so I'm going to put my 8 first, multiplied by 1 minus the rate, so 1 minus 1.10, to the number of weeks, so we're going to call that n for my exponent, all over 1 minus 1.10. Now, this formula can definitely be simplified, so I'm going to write this also as 8 times 1 minus 1.10 to the n over, when I subtract in the denominator, I get negative 0.1. So I can use this formula to find the total mileage over n weeks when she's increasing by 10% each week. Now I want to point out one other thing that's kind of an aside in this formula here. What I can also do, and we may encounter this in Algebra 2 Common Core, is write this total as a summation. We saw summations back in lesson number 3, where we said, okay, a summation means my total. Can I write it as a sigma? So yes, I can say my total Sn could be adding together each of the weeks. Now, how do I figure out how much she has each week? Well, the first week was definitely 8 miles. And then each week after that, I'm going to have to multiply by 1.10. Now, with my sigma, I have to use that as an index. So I am going to say, let's call my index the letter I. Now in week number 1, I actually don't want to multiply by 1.10. So I want to make that exponent be 1 less than what my I is starting at if I'm starting at the number 1. So week number 1 would be 8 times 1.10 to the 0 power, giving me just an 8. Because I want to do this for n weeks, my upper limit is going to be n. So I'm going to start with 1, I'm going to go to n, I'm going to figure out in each case how much she's running each week, and then the sigma says, let's add together all of those weeks. So I just wanted to point out another way to represent that sum. This problem specifically said use the geometric series formula, so that would be this one right here. But that's not to say on the Regents exam we might not see an application where we have to represent it as a sum instead. So here would be that answer using sigma. Now in part B, we want to find the total number of miles that she will have run if now we know we're talking 10 weeks. So that means in this problem we want n to equal 10. So 10 weeks is going to be my n value. So if I want to find the total, I'm going to go back to that first formula and I'm going to say S10 is equal to 8 multiplied by 1 minus 1.10 to the 10th power all over negative 0.1. Now this we can just go ahead and type into our graphing calculator. It does say round your answer to the nearest tenth of a mile. So for this one I see that 127.5 miles is the total number of miles that Kristen will have run if she does this plan for 10 weeks. Now obviously that answer definitely makes sense. Could I have started off and said, okay, A1 is equal to 8 miles, A2 is equal to 8 times 1.10 and get that answer. A3 would be 8 times 1.10 to the second power and get that answer, and so on until I get to A10 would be equal to 8 times 1.10 to the 1 less than what my subscript number is, because remember the first one we didn't multiply by 1.10. If I got all 10 of those weak answers, I could then theoretically just add all of those together and get what the total number of miles that Kristen ran would have been. Notice that we did have to, in Part A, represent this as a formula, so that does make it much easier work rather than finding all 10 of these answers and then adding them together. But isn't this a great way to check your answer as well? Looking at exercise number 3, we see that very often we have applications that include large numbers of something. In this case, it's the school auditorium. There are 10 seats in the front row. So if we know that that represents our front row, that's the A1 term, 10 seats. Each subsequent row, so that means every row, the next row, the next row, the next row, has 2 more seats. Now, since I know that I am adding 2 each time, what that tells me is that I have an arithmetic series this time. And what does that add 2 represent? That we call the D value. Each time I'm increasing by 2, I'm adding 2. Algebraically determine how many seats are in the whole auditorium if there are 30 rows. So that tells me I'm adding together 30 rows, so that's my n value of 30. Now think back, this has been a few days. When we did the arithmetic series formula, we always have to say Sn is equal to, this was where we paired the first number and the last number together, and we said, oh, there's n divided by 2 pairs, and then we need the sum of the first number and the last number. That was our rainbow arithmetic that we did a few days ago. Now, what I seem to be missing here is my an value. So I want to solve for A30. So to find A30, we're going to start with A1, and we're going to add n minus 1 times d. So we should be pretty good at this formula by now. 10 is my first term. N is 30, so this is going to be 30 minus 1, which is 29, multiplied by my common difference, 2. Adding this all together, we get that the 30th row has 68 seats. So, to find the sum of the 30 rows in my auditorium, we're going to say 30 divided by 2, multiplied by the first term 10, plus the last term 68. Now, when I go ahead and add all of that together, that's giving me an answer of 1,170. So that's my final answer for the number of seats in the auditorium. Now, just like the previous problem, there's also a way to represent this in what we call summation notation. So I want to just briefly talk about this. Our summation notation is our sigma, and we're going to call I the row number that we're on. So I'm going to say I starts with row number 1 and goes up to 30 rows. So remember what we have to do to find out how many seats are in each row. We have to take our original 10 seats in the first row, and we have to add, in this case, since I stands for the row number, I'm going to add on I minus 1 times the common difference. Notice that it works out really nicely when I is equal to 1. 1 minus 1 gives me 0. 0 times 2 tells me that no seats were added on to the first row. If we're looking at row number 30, 10 plus 29 times 2 was really that 68 that I found to be the 30th row of the auditorium. Now, to finish this off, we can simplify this and say this is the sum from I equals 1 to 30. If I distribute the 2 times the I and the 2 times the negative 1, putting together the like terms, I get 8 plus 2I. So if I just added together all 30 of those answers, I would get 1,170 as well. For our last application problem, exercise number 4, I want to introduce you to a formula that we're going to actually see more of after our sequence and series test. We're going to spend a day or two on this formula. So I just want to introduce you to the formula and show you one use of this formula. M stands for the monthly payment when we are talking about a mortgage payment. So for example, if you want to buy a house and you have a cost for your house, we have to pay each month a certain amount for the monthly mortgage. So we're going to look today at just a simple application of this monthly mortgage payment. And then next week we're going to be using it a whole lot more in a couple more application problems with both houses and even a car to figure out how much your payment would be. So let's look at the variables. We've got that M stands for the monthly payment. R stands for the annual interest rate. P stands for the amount borrowed. And N stands for the number of monthly payments. Now, don't get concerned here. You're not going to have to memorize this formula. Especially today, I just want to talk about how we enter the values in and how we solve a simple exponential equation using this formula. So it says the Banks family would like to borrow $120,000 to purchase a home. So if that's my amount borrowed, I'm going to say P is equal to $120,000. So that's how much they need to borrow to buy their house. They qualified for an annual interest rate. Now, when it says they qualified, that means that the bank looks at what their income is and what their other debts are and decides how much they can afford to borrow from the bank. The interest rate also is dependent on those factors. So in this case, we've got that the interest rate is 4.8%. So we're going to say R is equal to 0.048, converting over to a decimal like we always do. Algebraically determine the fewest number of years That'll be important because in our time, n is actually the number of months. So we're going to have to convert at the end from months back to years. We want our monthly payment to be no more than $720, so that's going to be our M value, 720. So take a minute and substitute those values into the formula, and that's as far as I want you to go. Then come back and look at mine. Now look carefully and make sure that you have exactly the same thing that I have written down. 720 is my M value. 120,000 is the P, the amount that we want to borrow. 0.048 every place that I saw an R in the formula. And we're going to be solving for N, so we left N in the equation. Now I went to my graphing calculator, and the first thing that I did was divide 0.048 divided by 12. Notice that that shows up 3 different places in my formula. So I'm going to go ahead and insert that. So I'm going to say 720 is equal to 120,000 multiplied by, when I did that division, I got 0.04. I'm sorry, 0.004. So this first part right here, 0.004. 1 plus 0.004 gives me this, raised to the n, all over 1.004 raised to the n minus 1. Now, I'm going to treat this like a proportion. So I'm going to say 720 really goes over 1. So I'm going to go ahead and I'm going to cross multiply here and cross multiply this way. And at the same time, I'm going to go ahead and multiply these two constants together. So I'm going to take my 720 and I'm going to multiply. So I'm putting a big bracket here. I'm going to multiply by 1.004 to the n and also by minus 1. So it looks like this. On the right side, 120,000 times 0.004 actually gives me 480. So I'm multiplying that also by 1.004 to the nth power. Now take a second and do the distribution. 720 has to multiply by both of these on the left side. So I now have 720 times 1.004 to the n minus 720 times 1, which is just 720. On the right side, I still have 480 multiplied by 1.004 to the nth power. Now I notice that 2 of my pieces have a 1.004 to the n. That's 2 different terms, one on the left side, one on the right side. We can consider those like terms because both of them have 1.004 raised to the n. So what I'm going to do is take this term right here and move it over to the left side, and take the 720 and move it over to the right. So I now have 720 times 1.004 to the n minus 480 times 1.004 to the n equals, and I move the 720 over to the right. Now you'll notice on the left side that these two terms are like terms because they have coefficients that are different. That's okay. But then they have 1.004 raised to the nth power. So I'm going to subtract 720 minus 480, and that gives me 240 times 1.004 to the n equals 720. I know this seems very complicated, but just follow step by step with me. Now, I want to get the exponential by itself, so I'm going to divide both sides by 240. And luckily, the numbers really work out nicely here. So I'm now to the point where I have 1.004 to the n is equal to 720 divided by 240 gave me a 3. Do you recognize this as one of those exponential equations that we had in the last unit? Remember when we had an exponential, we logged both sides? So we took the log of the left side and we took the log of the right side. With our rules for exponents, that allowed us to take that n and move it down as the coefficient. So now I have n multiplied by the log of 1.004 equals the log of 3. We always got the log by it, or I'm sorry, the n by itself by dividing both sides by the log. So that's going to be log of 3 divided by log of 1.004. On your calculator, go ahead and do that division. And my calculator gave me 275.2. But remember that that stands for months. We, of course, want years. So we're going to take that 275.2 and divide by 12. It gives me 22.9 years. We, of course, need a whole number of years, so that tells me that we're going to have 23 years to pay our mortgage back. Now again, I know that this was a very, very complicated calculation, but I wanted to show you how we could enter values into that mortgage formula and then be able to solve for one of the variables. So we're going to practice a little bit more with this in class, but then mostly we're going to be focusing on this equation next week after you take your sequence and series test. Thanks, have a great night, and we'll see you tomorrow.